Okay, let's take a look. If you have an alkene like this and that's being treated with hydrogen and platinum, what are the products? And the question is, what kind of alpha would you expect for the product? Realize that hydrogenation is a syn addition. Syn addition means that the hydrogen is either going to approach the double bond all from the top or all from the bottom. So if you think about it, the product that you're going to end up getting is going to be a meso structure, and hence the alpha is going to be 0. If you compare this to perhaps bromination, which I know you won't be asked, but still, if this was bromination, you would have gotten a bromine on top, a bromine on the bottom, and then the other one would have been a bromine on top on this side and a bromine at the bottom. So this would have been a racemic mixture, in which case the alpha would have been 0. So realize sometimes you might be asked questions which are going to go across 2 or 3 different chapters. Let's try to do a prepare question. Maybe if you want to generate butanol from 1 bromo 1 butene, how would you do that? Realize this is a vinyl halide, so of course at any given point of time you can treat this with KOH, and that will give you your alkyne. Now also realize from chapter on alkenes that alkenes will give you the aldehyde. However, what you need to keep in mind is that when alkenes go through ozonolysis and zinc and acetic acid, essentially OAC, when that happens, it essentially cleaves the bond, and so in that particular case you're going to end up with the carbon number less than what you start with. In this case, notice you have 1, 2, 3, and 4, and that's what you have here as well. And so what that means is that you would be able to simply add water, because that's one way to add an oxygen atom. So add water, but in this case the oxygen is going to go in the anti-Markovnikov fashion, and the reaction condition you have for that is BH3THF. That's the first reaction, followed with sodium hydroxide H2O2. That's first going to give you, that's 3, 4. That's first going to give you the enol, and then that's going to tautomerize to give you the ketone. Let's say my reaction is, maybe I have a ethyne, and I want to generate, I don't know, trans-pentene, trans-2-pentene. So trans-2-pentene means something like this. 5. I have 2 carbons already. I have to bring in 5. That means there's some kind of a chain elongation. Notice that the double bond has a substitution here and it has a substitution here. That means if I treat it with sodium amide, which is NaNH2, and treat it with 2 carbons first, essentially it's going to first remove the proton, get the acetylide, and then that acetylide is going to attack the carbocation. Bromine is going to go away. You would first end up with this compound. You do the same thing one more time with NaNH2, followed with CH3Br, and this time it's going to add the methyl group on the other side. So now this is the correct number of carbon atoms. All I have to do is convert the alkyne into the transalkene. In order to do so, the reaction condition you'll use is liquid ammonia with lithium metal, and that will go through the reaction, give you the desired molecule. Let's see. Suppose you have a fill in the blank, and the fill in the blank I have is, I'm just picking some random molecules that are coming to mind right now. You do have a tertiary alcohol and you're treating it with HCl. Okay, maybe water is present, so that shows you protic solvent. So it shows you that it's going to be some kind of a substitution reaction, and perhaps an SN1 at that. Whoa. An SN1 at that, because this carbon is a tertiary center. This is a protic solvent, and the fact that there is no heating, that tells you that there's going to be more substitution than elimination. So of course you're going to show the protonation for Cl leaves, and it's going to generate a carbocation, and a carbocation, like I told in class, it's sp2 hybridized, is going to be planar, and so now when your Cl has to attack, it can either attack from top or it can attack from the bottom, so you're going to end up equally likely one product with the Cl pointing upwards, another with the Cl pointing downwards. So these two together are going to make up the reaction mix. Okay, let's take a look at ozonolysis. Realize that if you have an alkene and you treat it with ozone and zinc and acetic acid as the second step, this is first, this is second, essentially that ozone is going to cleave off the double bond. Is going to give you the aldehyde in this case and propanol on the other side. That is to say that if you have a di-substituted alkene, you're going to end up with two aldehydes. On the other hand, if you have a tri-substituted alkene and under the same reaction conditions, one part is going to give you the aldehyde, the other part is going to give you the ketone. And if it's a tetra-substituted situation, so Let's draw a tetrasubstituted one. With ozonolysis is going to cleave right in the middle. You're going to end up with a ketone here and a ketone on the other side as well. So you should know what or how to convert an alkene into a carbonyl compound and vice versa. What I mean by that is if you are given, let's say, that your products after the ozonolysis are maybe these two, and you have to provide me what's going to be in the box, which upon ozonolysis gives you these products. So you're kind of on a retrosynthetic analysis here. What I want you to do in this case is first draw for yourself the aldehyde like I showed you in class. And now I'm going to use a thicker marker for that. Just join the two like that. So your product is going to look like 1H. This upon ozonolysis will give you the two desired products. Also recall that anytime you have some kind of an alkene, and if you subject that to osmium tetroxide, OSO4 pyridine, followed by sodium bisulfite water, it's going to be the cis diols that you're going to end up getting. On the other hand, if you treat it with MCPBA and water hydrolysis, it's going to give you a cis on one side, an OH on one side and an OH on the other side. That means it's going to be a trans diol. This was cis diol. And if you just subject that to KMNO4, then you're going to end up with carboxylic acids, because the cleavage of the bond will occur. So you're going to end up with carboxylic acids. Of course, we already did the ozonolysis. In that case, you're going to end up with an aldehyde for that particular case. It's in the nature of a cis diol that you can subject that to treatment with periodic acid. It's going to cleave off the bond in between the two alcohols, and it's going to also oxidize the OH into the double bond O. So you're going to end up with a dialdehyde. A dialdehyde, which is the same case that you're going to get when you carry out the ozonolysis of cyclohexene. So the two are exactly the same. I think that something else was brewing in my head. I wanted to essentially put into perspective kind of all the three chapters, so how you could do that. So let's say you have some kind of an alkene. Let's perhaps use 2-chloropentene, okay? And I want to convert it into 2,2-dichloropentene. How would you be able to do that? Realize you can't just, of course you can treat this with KOH, and that's going to generate an alkene. But if you treat this with HCl, only one HCl can add. So an H on this and a Cl on that side is what is going to be obtained. But you want both the chlorines on the same location. So you somehow need a situation that you're able to put in 2 chlorines so that at a later time you can deliver 2 chlorines. So let's say if you treat this with 2 chlorines, chlorine first, so that you end up with 2 chlorines on the product, and now subject that to 2 moles of KOH, and hopefully you can see that that's going to give you the alkyne. And now if you treat that with 2 moles of HCl, essentially H and Cl are going to add up in a geminal manner. You're going to end up with the gem dihalide, and that will be your product. You could also be asked, given 2 structures, perhaps COOH maybe an OH and an H and an H and an OH and a CH2OH. And I'm comparing that with, so maybe I should just put versus. Whoa, versus. A COOH, an OH here, an H here, OH here, an H here, and a CH3. And now you have to tell me what's the relationship. Are these enantiomeric? Are these diastereomeric? Are these meso? What's going on? Realize these are not meso because if you draw a plane through it, it doesn't quite divide those into two equal halves. These are not enantiomeric because, well, the groups themselves are different. So these really are not isomeric at all. But if you wanted to, if they were, let's say it is actually a COOH, so maybe let's change this to carboxylic acid. COOH. And a COOH. And now somebody asks you what's the relationship between these. All you got to do is draw a mirror curve, draw a mirror plane between, and see if those are mirror images or not. And looks like they are. One way to do that is just for the Fisher, just basically look at the mirror image, whether they are mirror images or not. Alternatively, you can determine the configuration about the two chiral centers, and if they happen to be opposite of each other, essentially you can say that these are mirror images of each other. So let's just work on one. This is highest priority, followed by COOH, followed by the third one. Looks like you want to go in the anti-clockwise direction, but hydrogen is horizontal, so you're going to call this an R. Likewise, when you do the same thing for the bottom carbon, you're going to go in the R direction, but again hydrogen is on the horizontal direction, so it's going to be S. So since top one is R, bottom one is S, you're going to say that these are going to cancel off on each other. If you do the same thing for the other molecule, if these are R and S, and if these are enantiomeric, you should expect these to be S and R. Let's take a quick look if that actually is true. So if you're going in the R direction and hydrogen is horizontal, so it probably is S, which matches what I had predicted. And the same thing goes for the bottom one. This is 1, this is 2, that's 3. So 1 to 2 to 3. That's actually an S, and since hydrogen is horizontal, that means it's going to be an R. Okay, let's do a couple more. Let's say you have, and I'm doing this in an asynchronous manner and kind of out of order also, because I want you to be thinking if it's a, based on the reaction condition, based on the question, how should you be thinking? What should be your plan of attack? And maybe THF. And you have to predict the product. Realize in this case that you have an aprotic solvent. What's given on the arrow, which is the T-butoxide, it's not a very good nucleophile. It is a base. A base with something which is ready to leave. That means it has set the stage for an elimination reaction, irrespective of whether the heat is there or not. And so all you're looking for is, since this is a really good base, all you're looking for is a hydrogen and tie to the bromine. And as that bromine leaves, the hydrogen electrons are going to move between the carbon-carbon bond. The base is going to go away with the hydrogen, and the product you will get is this. Realize in this particular case, since this is an E2 elimination, it doesn't quite generate the carbocation, and that is the reason why you are going to see, in a concerted manner, you are going to see the generation of an alkene. In this case, it happens to be the less substituted alkene, but that's the only possibility, so we are okay with that. Okay, let's try another one. I have a bromine attached onto a ring. We have a T-butoxide. Again, THF, you have to predict the product. In this case, since it's a T-butoxide, again, that's a great base. It's not nucleophilic. So this is going to be an elimination reaction. Realize, since this is a strong base, it would want to incorporate E2 type of elimination. So in this particular case, you would not be able to get a product from this side. You would rather incorporate the other side for elimination for the E2, and this is going to be our product. On the other hand, if you would have used a weaker, somewhat weaker base, something like, let's say, maybe a lower concentration even, 0.01 molar if it's specific, then you can perhaps envision that you are going to end up with a carbocation, right? And that carbocation will then be subjected to a hydride shift, carbocation here, and then it will give you your alkene, like that. Okay, let's continue with another one. I have a mechanistic type problem. So I have an isopropyl group on the solid. I have a Cl here, and I have a CH3, and I'm treating it with a good base in presence of ethanol, and it's generating. Your isopropyl is still in place. Here's your double bond, and here's the CH3, and you have to provide the arrows as to how the reaction is occurring. I think the easiest, I don't know about you, the easiest for me would be a chair. Otherwise, you can perhaps envision that if you need the leaving a group is here, that means for it to be anti, the H should be here, or there should be an H over here at the beta position. Hopefully that's what I would expect. Now compare the structure to what you have. The H clearly is absent in this case because you have a big bulky isopropyl group. So the E2 elimination for a good base, and by the way, we were also heating it, the good base and the E2 elimination is not possible in this particular case. The only one that can be used is going to be the H on the other side, which is going to, let's pick up the proton, electrons will move, the Cl will go away, and you will end up with this structure. And that's it. So if it's a mechanistic question, let's say for 3 points or something like that, think about it. Think about what the substrate is. Think about what the base is, whether it's heated, whether it's a protic solvent, whether it's, I mean, what's going on essentially in the reaction. Good base automatically means an elimination is going to take place, and or if it's a good concentration of the base, that also means E2 elimination will take place. Let's say if you have bromine, maybe 2 methyls here, and I'm treating that with water, what the product would be. I'm not heating it, so that means it's some kind of a substitution. Since it's water, it's protic, that means it has to be SN1. SN1 means you're thinking about drawing carbocation, so the carbocation that will be generated will be here. It's connected to 1 carbon, 2 carbon, and a 3rd carbon. That means it's a tertiary center, and is also allylic because it's resonance stabilized. So resonance is ongoing over here. That's what you have. And so when water attacks, you're going to end up with, whoa, this molecule. So here I'm showing you the reaction between the 2-iodobutane and treating with ethanol. Realize that it's going to be SN1. The reason why it's going to be SN1 is because it's a protic solvent and the nucleophile is not very strong. Realize it's secondary, and that is why we are taking the time to go over the rest of the reaction conditions. Otherwise, if it's primary or tertiary, in that case it's going to be SN2 or SN1. Pretty severely clear. And so in this case, you're going to end up with a secondary carbocation. So show the generation of the carbocation, just because you know now, you have figured out that it is going to go through an SN1 reaction mechanism, and that means that it's planar, so the attack can occur from top or bottom, in which case you're going to see these two structures and the proton will be lost with the reaction with the iodide to give you the two desired products. Okay, you could also be given some structures and the kind of question that we did in class, that if you're given maybe a primary halide and a secondary halide, and you're asked which one has a greater tendency to go through, let's say SN1. You would know that it's the second one, the secondary one, because the secondary will give you a more stable carbocation. If you do the same thing with, let's do another one, just so that we can put things in perspective. So in this case, of course, again, it's going to be the second one, because the carbocation that you're going to get is a resonance stabilized carbocation. Resonance stabilized. So that's the reason why you're going to end up with an SN1 for this particular case. So yeah, expect those kind of questions in the test as well. Occasionally you might be asked like a explanation, and I mean, this goes back to what we learned in class. So you could be given that if you treat, let's say, an alcohol treatment of 1-propanol with sodium bromide, that does not give you the alkyl halide, whereas if you treat it with HBr, you do get the product, and you have to explain why. Any ideas? Well, realize that if you were to seek the first case, you would be saying that OH is the leaving group, because Br negative is going to be your nucleophile, and you know that OH is a bad leaving group, poor leaving group, because the conjugate acid of that is a weak acid. On the other hand, if you treat it with HBr, essentially you convert the alcohol into a better leaving group by just protonation, so that's ready to leave, and since it's primary center, the Br is going to attack and the OH is going to leave both at the same time, and so this is via an SN2 reaction mechanism. Polar aprotic solvent will support this, and you're going to end up with a Br, and I'm going to write it this way so that you show that the bromide is coming from the back. So realize a couple things. I mean, you could be given this in the form of a case study, and maybe reaction A, reaction B, why doesn't A occur? Explain that for 2 points or something, and then you could be asked questions on what kind of solvent would you put in this particular case? Would you put water? Would you put ethanol, C2H5AOH? Would you put acetic acid? Or would you put something like ether? Okay, and you know that you're looking for a polar aprotic solvent, so ether should be your optimum choice. The attack has to be a backside attack. It will go through an inversion of stereochemistry. If this was a chiral center, that means R is going to get converted to S is going to get converted to R. If you are to comment on the rate law is going to look like rate is equal to K times concentration of the alcohol. I'm just going to write that as ROH times HBr, because that is where your nucleophile is. So that's going to be your rate law. It's going to be dependent on both of those reagents.
Let me just do one last thing, and that is that if you have perhaps a vinylic position, you have a B here, you have an I here, and you're treating it with NaCN. So CN negative is your nucleophile. Realize there's two leaving groups here. There's a bromine, there's an iodine, but also realize that if you have a vinylic position, that is not going to go through an SN2 reaction mechanism. This is a polar aprotic. That's a good nucleophile. That's an SN2 reaction condition, and the vinyl position does not support the SN2, so it's the Br that's going to leave. So your product is going to be the CN. One will be this, the other will be SN2. If for some reason this would go through an SN1, so let's say you were treating HCN perhaps with water, in that case you will try to show a full positive charge, which by the way is resonance stabilized, and so electrons will move, creating a positive charge, which is where the attack of the nucleophile is going to take place. I think that'll be all for today. This is about 31 minutes already, but study well. Good luck. If you have any questions, feel free to email me, and hopefully everything will settle in for all of you. All right, I'll see you Thursday. Bye.